There are, and what we're going to look at in this course is turn on and turn off snubbers. What do snubbers do? They delay the rate of rise of voltage or current in a device in order to keep the transients within the safe limits of the device, and can also be used to minimize the power dissipated during the switching times by means of wave shaping. Section 6.3, the first paragraph. Now, we're going to look at the mathematical modeling of a turn off snubber. In this case, the device that we are going to protect is that transistor, and the snubber is a passive snubber consisting of a capacitor and a resistor. In order to retard the rate of rise of the voltage when this device switches off, we need to use a capacitor in parallel to it. But if we have the resistor in parallel, in series with the capacitor in parallel to the transistor, then we're going to have a voltage that consists of the R and the C. And what we want in parallel with this device is just the C. So while the capacitor is charging, we are bypassing the resistor via this diode here. Here is an inductive load, and there is a flyback diode. Now, the circuit as we have it here implies that we're going to switch this device on and off, and we're going to do this at a very high frequency. So, such a high frequency that the load current will not change substantially in a cycle of switching on and off. So what will happen here is the current I that is flowing through the load will either be flowing through the diode or it will be flowing through the transistor. But it stays a constant. And because we are switching on and off, we will have current being shared. That I there will be shared between the transistor and the diode during the switching time. Now Vt here is the voltage over the transistor. V is the voltage that is supplied to the circuit. IT is the current flowing into the transistor, and IC is the current flowing into the capacitor. And I is the total current. So if I look at I, it will be I transistor plus IC coming together at this junction here. One of the assumptions that we have to make is that the current will fall linearly during the turn off time, and T2 is our turn off time. The capacitor, the transistor voltage will rise until it reaches its maximum, which is the supply voltage there. So when Vt is equal to V, then we have the situation that the device is completely off. And at that point then, the current will be flowing, will be circulating like that there. But I stays constant the whole time. So, and there is the level of I being indicated. Now the first thing that we have to ask ourselves is, when will this situation occur that I have indicated to you here? That the current will be, I will be flowing through the diode. Well, that will happen when, if we look at this as an ideal diode, when the voltage over the diode is equal to 0. When will this happen? It will happen when Vt is equal to V, because then we will have V minus V gives us 0. When does this happen? It happens at that point there. There Vt is equal to V. So the diode will switch on. Will switch on at T1. Now we must now derive an expression for the Snubber capacitor so that we can do the design calculations for this capacitor that will delay the rise of voltage over the transistor to its off-state value of V in a time of T1. Now I said to you that we can minimize the power dissipated during the switching time by means of wave shaping. Now by shaping the voltage as it is here with this dashed line, the power dissipated in the device is equal to Vt IT. If I can keep the voltage close to 0 until the current has dropped to less than 50%, then I can reduce the power to around about 30% of what it would have been, or less than that. So that is the whole idea of designing a value for the capacitor, that it will be such that we will reduce the power dissipated in the transistor during switching time. Now you can say, well, why now reduce the current during switching time? What about when the device is on and when the device is off? The problem is that when we increase the frequency at which we are switching this transistor, the voltages and the current during the switching time cause power losses in the device that can exceed that which is dissipated in the device while the device is on. And so minimizing the losses during switching is a very advantageous route to go if you think that all you need is 3 components: a diode, a resistor, and a capacitor. Otherwise, you'll have to use a heatsink to get rid of the heat. So now we are there. Derive an expression for the Snubber capacitor C that will delay the rise of the voltage over the transistor to its off-state value of V in a time of T1. Now when we look at this current of ours there, the current IT, we can see that it is linear. So it is given by Y is equal to mx plus C. What is the value of C? It is where we cut the y-axis, so that will be I. What is X? X in this case will be T. What is M? M is delta Y over delta T. So if I now look at my graph, I see that the change in T is T2 minus 0. So then it will be T2 below the line here. When I look at delta dy, it is the change in current. So it will be I minus 0. So I'll have I over T2. That gives me M. So if I now rearrange all of this and I say that Y is IT, then I can rewrite this thing as follows. IT is equal to T over T2 times I plus I. Is that true? Is it true or not true? What did I do wrong? Okay, the M, the delta Y, was negative because it was 0 minus I, because the slope is negative. So I should have had a negative here in front here, and that is still positive. So when we go to that first equation there, IT is equal to I minus T over T2I. We now know where it comes from. Then the next thing that we can do to the circuit, we can apply Kirchhoff's current law to it. Now Kirchhoff's current law, if we go and look at this node here, it is the current IT and the current IC that will together form the current that is flowing away from the node. So I is equal to IT plus IC. I is equal to IT plus IC. So if we now go right up to T1, we can say that IC is equal to I minus IT. Now at the time T1, Vt is equal to V. If I look at this here, Vt at T1 value is equal to V. At T1, Vt is equal to V. Therefore, at T1, the charge Q on the capacitor is given by Q is equal to CV is equal to the integral between 0 and T1 of IC dt. So it is the function of the current that was flowing into the capacitor. And if we substitute equation 6.1 and 6.2 into equation 6.3, we have that CV is equal to the integral from 0 to T1 of I minus I plus T over T1I. That one and that one cancels. So therefore we have that it is equal, and I does not change, the value of I, so it comes out of the bracket, is equal to the integral from 0 to T1 of T over T2 dt. If we divide both sides by I, then we cancel it here and we have CV over I. CV over I is equal to T2 over 2T2, because the integral of T is T squared over 2. So we have T squared over 2T2 between the limits of 0 and T1. If we then fill in the upper limit and the lower limit into this term and subtract the lower limit, we get that it is T1 squared over 2T2. Is everybody happy up to there? And from this, we can have an equation that says C is equal to I T1 squared over 2V T2. And there we have the equation that we set ourselves to do. But this snubber of ours, we want to have wave shaping so that we can minimize the power that is dissipated in the device during switching. So this T2 is fixed. It has got to do with the transistor. And if I now go and I look at the 0 is fixed, that's the time when I start switching off. I now see that the only thing that I can move around is T1. I can design C for a certain T1, because if I go and look here, I see there is T1 squared. So if T1 is smaller, then the cap is going to be smaller. If T1 is larger, then the cap is going to be larger. And I want an optimum value for the capacitor. So when I look at the definition of switching loss, I want to get an expression for the switching energy loss in terms of V, I, T1, and T2. And if I look at the switching loss, now previously I used E there, but it was confusing because it let you think of voltage, DC voltage. So the scientists for energy use a W. So the switching loss by definition is the integral of the product of the voltage and the current. And that is the area under that curve. So we now need an expression for Vt up to T1 because we want to use this equation. We've already got an expression for I. That is the transistor current. We have that one. So how do we start? We use the expression for the instantaneous charge on a capacitor. Which is Q is equal to CVT and therefore Vt is equal to the charge over the capacitor divided by the value for C. Substituting equation 6.3 into 6.5, the integral of IC dt is equal to the charge on the capacitor that we got previously, so we can say that Vt is equal to the integral of IC dt divided by C. If we substitute equation 6.4 into 6.6, and that is the value for our capacitor, so we are going to replace C with the expression that we got for C, and then we substitute equation 6.1 and 6.2 into equation 6.7. We get that Vt is equal to 2Vt2 over IT1 squared, and the integral of I minus I, those two cancel each other, plus T1 over T2 I. And if there is a typo error in the book there must be an I there before the last term. And if we manipulate everything here, the I's cancel, and we have that Vt is equal to V times T2 divided by T1 squared. So now we have an expression for Vt. If we now substitute that into this equation for the switching energy loss, and you manipulate and everything, then you get to the following equation, which is that the switching energy loss is equal to Vi times T2 over 2 minus 2T1 over 3 plus T1 squared over 4T2. But if we now look at our circuit, At the end of the switching, the turn-off period, the capacitor has charged up to V. That is the voltage over the capacitor. The energy that is in that capacitor is equal to a half CV squared. What is going to happen when we switch on again? The capacitor is going to discharge through here. It cannot discharge through the capacitor, so it's going to go through the resistor. And all of this energy is going to be dissipated in the resistor. So the energy that we put into the capacitor to minimize the energy that is dissipated in the device is already lost. So this snubber is called a dissipative snubber. The energy that we store in it to reduce the transients and to do the wave shaping is lost. So one does get non-dissipative snubbers, but they are much more complex than this one. They involve taking the energy that is in the capacitor. When you switch on again, that energy is transferred back to the source. Two over 3 T2. I've got a worked example here. A transistor has a switch off time of 3 microseconds and carries a current of 60 amp. The supply voltage is 120 volts. Determine a turn-off snubber capacitor for the transistor. Design the capacitor for a minimum loss in the transistor. So for a minimum loss, T1 is equal to 2 over 3 T3. So that gives us that T1 will be at 2 microseconds. Fill in your T1 and T2 into your equation and you get that the capacitor is 0.333 microfarad. How do I ask this question in a test or an exam? Well, this one is about 3 marks. This one here. But usually I want about 20, 21 marks out of it. I can't ask you to do the derivation because that's a low order question. So I have to ask it in such a way. I say design or answer this one and derive any equations that you use. So which equations have you used here? You've used that one. So most students only give me that one there. But what is this one? Isn't that also an equation that has been used? So this first one will give you 6. This one here will give you 12 marks. Do you understand the way that you have to think? Think clearly.